All right.
Everyone doing?
Mm. So I guess I should be thinking about semi-ring dictionaries. Uh, I've been uh, I've been focused more on chapter 13 of SOFP because the section that we've been working on is so closely related to what we are doing in the other track. And so
Hmm.
that's I'm more excited about that at the moment.
Which section is that? The I didn't look at it, obviously.
It's
I
Hi,
morning.
morning everyone.
13.2 and 3, basically, I think is the, see, 13, oh no, 13.3 is free constructions for other type classes, meaning other than monad. So 13.2, I guess, is basically where Sergey is going through the various possible encodings of the free monad.
right.
And 13.1 is where he's giving an extended example with of how you do a monadic interpreter.
Hmm. Yeah.
So for for anyone who isn't able to attend the other track, I think Charles got around to putting our last couple of meetings through putting up the recordings. So if you are interested in seeing what we're doing there, then the links to the recordings are on the meeting pages.
Yeah. It's an interesting track.
Yeah.
I watched the lecture video, but I didn't attend the meeting series. I mean,
Mm.
how was the discussion? That looks like you guys are still going through the first lecture.
Yes, yes, still working our way through the notes on the first lecture. And so there's a total of 4 lectures in that
Mm.
class. At this rate, it will take us some time to get through the whole thing. But by the time we do that, we might actually be able to understand something interesting about it. So, I
Yeah.
mean, for me, it's starting to come into focus what the relationship is between their magic effect type and the monadic way of handling effects. What what I'm still really unclear on is how the composition of their handler-based effects, which looks a lot like nested exception handlers. How does that relate to something like monad transformers as a way of composing effects? So
Yeah. So
yeah,
that's something we could talk about. I was thinking a lot about monads and those things and sort of recently came to the conclusion that monads maybe aren't the right way to think about them. Um, because these handlers take continuations and return monadic values, but they're not monadic values by themselves. So it's harder to compose them.
well,
Mm.
right. Well, if you understand the continuation as the function argument to a bind or flat map, uh, then I think it is very much the monadic style. Um, the thing that
style.
is,
Yeah.
yeah, the thing that is different in their handlers is that they sort of glue together the handler for bind and the handler for each operation. But otherwise, I think it's pretty much the same idea as in, for example, Sergey's runner in the example that he gives in section 13.1.
Okay.
So I haven't quite figured out. There's some kind of rule for how you thread through the handlers. And I mean, Pete, you gave an example on the Slack that looks as if it's doing that, but I haven't quite figured out sort of what is the general rule for, when do you need a handler? When do you need to pass it on? And when does a handler need to be stacked on top of another handler that handles something that the first handler doesn't handle, and so on and so forth.
Right.
But,
Yeah. Let's talk about it. What is it? Next Monday? Or
I think it's a week
from
9 days
Monday.
from now.
Yeah.
Okay.
And we could talk about it more on Slack. I just think,
Yeah,
maybe this isn't the place.
probably not. But if this serves as a teaser for anybody who wants to go watch the videos or read the papers, then I recommend it. Because
Yeah.
it seems like it's maybe requires less conceptual load than a system with lots of different monads and monad transformers, which I have trouble wrapping my head around. But if you can understand nested exception handlers, then I think maybe this effect handler way of doing things is easier to get a hold of.
Yeah. Yeah. And I think it's got a lot of value to me because, having a purely functional language is nice, but it's not, in some sense, it's not reality.
Right.
Because you're
Some
always
point
wanting to change things and deal with the outside world and all that sort of stuff. And
right.
so, but this makes it look sort of like you're doing things like mutation or doing IO in your program, but it all gets translated in a way to something that's purely functional.
Right. The the effect handler way of doing things is it's maybe more expressive than the monadic way of doing things because the type is on a per operation basis rather than typically for the monadic way of doing things, you have a single type for several different operations, and you handle the monadic type constructor for all of those operations or none of them. Whereas the effect handler way is a lot more a la carte.
Yeah.
Anyway, so we were looking at the Semiring dictionary paper. I think we were at section 3.3. Is that the?
Yeah, I guess so. I was reviewing Slack and Hugh had some questions, which I guess were before our previous meeting, but I'm not sure to what extent we answered them. And let's see. I have maybe a couple of comments from before. Yeah, just an observation. Does somebody want to share, or should I share my iPad? Or
If you have it handy.
let's see if this works. Ooh, it moved over here. Okay. So I was noticing, let's see, this rule here, which is about multiplying things. And basically this rule is saying that if you have basically two semi-modules, you can multiply them. And I think I hadn't really wrapped my head around that, but the semi-modules include things like their dictionaries and sets and records and combinations of those things, right? So basically you can multiply them all. So you can have a dictionary, like a dictionary of reals, and then have another record with real values, and you can multiply them and you get a dictionary of records where you multiplied all the values out. But then you can multiply dictionaries and dictionaries where you get a dictionary with nested dictionaries, or all these different combinations of things. And I think that gets powerful, especially when we look at like maybe some of these aggregation operators, because you're sort of multiplying things together and then summing them up. And you can always sum up these semi-modules because the semi-module has to have addition. So you can add up all these different kinds of things and multiply them out and things like that. I don't know. Does that make sense?
It does make sense. And yeah, I think that's where this system gets a lot of its power, as long as the thing you want to know is expressible in terms of that sort of multiplication.
Right. Yeah.
So-
I mean, a lot of these things require you to be based on the same, whoops, I'm pointing at my, basically they have to have the same semi-ring,
Right. Yeah.
as their base, which is something like real or int or whatever. So your dictionaries all have to have those kinds of values, or semi-modules based on those kinds of values. So
So I
eventually
wanna,
you get down to multiplying in the semi-ring when you finally get down to the bottom. But yeah, you or
Yeah,
somebody?
That sounds right,
One-
but I think Nue had a question.
yeah, so just, I get lost in the details on this because it sounds like when you talk about rings it's like abstract algebra stuff, I assume. More like,
Yeah.
so, I'm vaguely familiar with that stuff. So, but on a more, I guess, zoomed out conceptual level, I just want to maybe you can answer this question. So when you say, so this is the title of this paper is like semi-ring dictionaries. So I suppose there's like a ring dictionary and semi-ring being like, are there basically conceptually, is this a looser constraints basically? Is that the general
A
approach?
semi-ring is like a ring has all these operations and then a multiplicative inverse. And a semiring doesn't have that. It just has, you know, addition and multiplication, 0 and 1, and
So it's less constrained,
yeah,
Yeah, it's a little weaker in that sense.
weaker,
a little
yeah.
weaker.
So
Or
that,
more general. Yeah.
so
Right.
that allows more practical application, I assume?
Yes, because you can make something, as they show in the paper, you can make something like a dictionary into a semi-ring. And I don't think you can generally invert a dictionary or find a multiplicative inverse for a dictionary. So if you added that constraint, then you wouldn't be able to use dictionaries the way they do.
Okay, okay.
I think what I remember is the first interesting example of a semi-ring is the natural numbers.
Yes.
Not a ring because you can't subtract them, but you can still add and multiply, and you have all of the laws that you would want for those two things.
Okay.
Uh,
Going back to Peter's, like your example right here with multiplication,
Mhm.
right? I don't know the details of those symbols, but is it some type of like cross product or something?
You're talking about this one over here?
Yeah.
Yeah. Yeah, that's their tensor product thing. But yeah, think of it just basically as a cross product, that you're taking one of these and multiplying, you know, one of these is of that type and one of these is of that type. And when you multiply them together, you're basically getting roughly pairs, but it's not quite that. Like if you have a dictionary where your keys are T1 and your values are T2, then your keys will still be T1, but all your values will be,
Those
you know,
products.
T1 the cross product there. Yeah,
Yeah.
the vector,
Okay.
the tensor product, whatever they call it. Yeah, that's a little detail that gets a little hard to follow, but
Yeah, so I think like for myself, it's like when I look at the symbols and stuff, it's Greek, but in terms of like at least trying to get out of this the general concepts, it's you know it's useful to me. At least it gives me some way, a bit of a handle to at least grasp some of, at least increase my understanding somewhat. So I appreciate that.
yeah. That came, but anyway, that was one observation. So I think in Slack, Hugh had some questions about, you know, this nesting on the right. Did we answer that?
I think we did, yeah. I
Sufficiently?
think because
Okay.
like Young Il was talking about this as it's basically syntactic, right? They're like quotation marks. So the idea is that
Right.
you can take an expression in whatever it's called, NRC plus, and then render it down into SDQL by repeatedly applying these rules.
Yeah.
Right.
Recursively.
Right.
Yeah.
Yeah, this is a recursive function definition where the function translates from one language to the other.
Yeah.
So I was wondering about flatten, because I'm used to flatten as sort of a monadic operation, you know, where flat map or bind is the same as map followed by flatten. But I think all this is doing is you have some sort of dictionary type thing. When you translate E, you have some sort of dictionary-ish thing, and you go through each entry in the dictionary with the key and the value, and then you just multiply the value times the key, and then you sum all those things up. So this might be where, you know, some of what I was just talking about with the multiplication makes more sense, because these keys could be fairly complicated things. They could be a dictionary where the keys are dictionaries or something like that, right? And, you know, so like if you have a bag that, you know, where the keys are some interesting data structure, and then the value is just how many of them you have. When you sort of do this sum, you'll sort of take all the keys, those interesting data structures, you know, scale them up by the count, and then add them all up. And if they're semi-ring dictionaries, all that stuff makes sense for pretty much any semi-ring dictionary. At least
So
it
wait,
makes sense type-wise. I'm not quite sure why it's called flatten, but
does E is some kind of dictionary here, right?
I think so, yeah.
That has keys and values. So yeah, I don't really get this. So if let's say it's a dictionary from string to natural numbers,
Yeah.
then
Well, you
so when
can't multiply strings by numbers, I guess.
that's what I was wondering about. I guess okay, so they are not. Oh, okay, and maybe the reason you can't do it is that they're not both semi-modules over the same semi-ring. So it probably doesn't make sense to do multiplication in that case. You need to have the same base semi-ring in order for that to make sense.
Right.
I suppose you could have the keys and values both being, let's say, integers, and then this sum is an actual straight ahead sum.
Yeah.
But it's
Right.
hard to imagine
That's
why
sum
you
of
would want to do
products.
that.
That's sum of products, right? Flattening.
Yes, certainly looks that way.
Yeah. Yeah. It'll sum up these products.
So what do you,
But
what is achieved
but
with that?
remember that summing things depends on what the type of this thing is. So yeah, if they're just ints, you'll add up all the ints. So if you have a dictionary from int to int, they'll create a dictionary. Oh no, it won't. It'll just go through, take the product of each pair and sum those up. But I think maybe it has more to do with this idea of these nested relations, where you have each row in your relation contains basically a set. I think it's a set, right? And so maybe in that case, when you do a flatten, then it will basically end up, instead of having a relation with a relation in it, you'll just end up with a relation somehow. But I'm not sure of the details.
It looks, I mean, would scalar be appropriate synonym for flattening? That's my impression. A single value.
Um,
I think they reserve the
well,
term scalar for things like natural numbers and real numbers. And so the flattening doesn't necessarily result in one of those.
yeah, so if everything here is a number, then it's just your regular,
Yeah.
you know,
Yeah,
big
I'm not
sum.
saying,
But this K could be something more complicated, like a dictionary itself, right? In which case you're scaling up all the values in the dictionary and then adding up the dictionaries, which
yeah, what do you get out of that? Like what's to what purpose, or like,
Yeah, that's a good question because it's easy to see how this would work if v and k are both integers, but I can't think of an actual case where you would ever want to multiply keys by values. Has anyone ever done that?
Hmm.
As numbers.
Yeah. Yeah, it's like, yeah, like their example up here doesn't seem like I can apply this to that or something. So yeah,
oh,
it's not.
Sorry, go ahead.
maybe if you can compare different flattened dictionaries, and you just get like a kind of almost like a gross metric to be able to, maybe that could be one of its use cases. That makes sense? Did I say that correctly?
It's true. Maybe it kind of assesses the size, like an overall size.
Mm,
I would assume one example, just using expand Peter's example a little bit. The key is a dictionary, and then V is a multiplier, say, and then if I just say K is a department salary dictionary, and then there are multiple departments, and then V is the multiplier, saying I decide to boost the salary of different department by different scale. Then this operation would give me the whole company's salary after the adjustment, and still indexed by all of the keys, which will be all the employees in the company. That's just, I'm imagining the use case, which seems to me is just a convenience of a database operation. But I don't know if it's something that is more general than that.
mm,
Right. I think they're giving us some examples in this paper of the sorts of data sets to which these operations can be usefully applied. But most of us aren't used to thinking in terms of that kind of data. So I think we tend to have questions about, well, how useful is this exactly? But if we were more accustomed to thinking in terms of these sorts of databases, it might be obvious to us.
Yeah, I feel their design is heavily geared toward database handling complex databases, and then maybe it's their value there, but I'm nowhere close to be an expert on database. So,
Yeah, nor I.
yeah.
I feel if I knew a little more genetics, then their example would make more sense.
Yes.
Yeah.
The image looks wonky to me. Is that just me or?
I think it went to sleep again, or it.
Oh, did I?
What does it do? It
Thank you.
iconizes
Is that
itself.
better?
Yes.
Sorry. Yeah. So I noticed at the end that there's some additional stuff that's kind of useful. So they kind of give more words around things. Flattening is only performed an input parameter that is nested. So like the input could be a dictionary where the key is a dictionary. And you union the keys, but first you multiply them by the bag, the value, which is because I guess it's a bag. So in that case, the value is just a count, I guess, but still not sure why that makes sense. But I guess, yeah, Wing's example might make sense where you're just scaling up, I don't know, salaries or something like that, and then trying to create a bag with the resulting information.
Yeah, that does make sense. I have another random question, if you don't mind skipping forward a bit.
Okay.
Trying to figure out how this thing actually runs. And apparently it's a mixture of Scala and C++.
Where are
Uh,
you looking?
yeah,
What
sorry.
page?
Moment. Section 8, so page 19. Yeah. Compiler toolchain is written in Scala. I'm looking up at the top here.
Hmm.
And then, so
So I guess
you,
it's generating C++.
yes. I'm having a little trouble imagining this. So I guess there's a there's a data store, and you send a query to the data store. The query gets compiled with these Scala tools into C++, and then I guess it runs the C++ and gives you a result from there.
Right. So I think they're saying the compiler is written in Scala, but it generates C++. So you give it your program, Scala will translate it into C++. And then C++ has a runtime that includes these dictionary implementations. And does that make sense? I haven't really read this.
I think so. I think so. All right, I just wanted to make sure I was understanding it right.
That's kind of an interesting question. Like why this kind of Scala to C++ translation?
I assume it has something to do with efficiency, and they are trying to custom generate code for each query so that it will run as fast as possible.
Yeah. Scala, runs on the JVM and has garbage collection, but you can do C++ where objects are allocated on the stack. And so you don't need garbage collection. I don't quite know how they do that, but I know you can do that in C++. And so presumably they're doing it for efficiency. C++ will compile down to C, which then, generates fairly efficient code. So there's a lot of tools around C++. I
So it's
guess
more
that
for
makes it.
speed optimization then, huh?
I think so.
Oh, because I assume it's just really large, data sets, basically? That's why?
Yeah, I mean, I don't know how you can get away with all these objects being stack allocated when they can be so big. But
Well, I think C can handle a stack that is basically as big as all of memory. Well, pretty big anyway.
yeah,
Yeah, I would think so too. I think it's the allocating the objects in a stack instead of the heap. It's probably just reduce your interaction, so it's faster. It's not really about the memory size thing.
yeah. No, I'm just more thinking in terms of like, just how do you, well, just in terms of like you're doing these expressions and computing intermediate results and so forth. But I guess it all works. It just goes on the stack use the intermediate result, and then somehow you have to go deeper, go back in the stack and fill in something that's already been pre-allocated, because otherwise you're not, you know what I'm saying? If you generate a temporary thing and then from that generate something else, then when the stack pops, you know, you want to get that temporary thing out of there. So you want to pop it out, but you've got this, your result is further in the stack.
Oh,
So,
I see what you mean. You're saying that the stack you can always access from the top. I don't think by the stack that is used in C++, that's in man that way. Stack is, if I understand correctly, is actually in a function scope that you create a stack, and then but you still have pointers deep into a stack. You don't have to go all the way from the top search for it.
Right.
You can access just like at a constant time instead of a linear time.
So you
Uh,
can access the stack almost like an array. Is that what you're saying?
I guess yeah, you can say for access they have a special structure to help you access quickly rather than just doing a traditional stack that you always have to access from the top. That's what a compiler does for you. And then yeah, so that would I guess it's a data structure choice, and then it's stack is the way that you kind of have pick a data structure that is working for a scope that once you get out of scope you can just erase it, kind of thing.
But
It's
like,
Right.
I mean, I don't see if that was the case of like kind of almost like random access on stack. It's like, why even call it a stack then?
because it's really handled as a stack by the compiler. It's
Right.
they build it.
The stack discipline is not so much for accessing data as it is for allocating and deallocating data.
Mhm, yes.
So, because you can always pass the address of something that is farther down the stack to a function higher up on the stack.
That's correct. Yeah, that's a good way to put it. Thank you.
Say that again. I'm not familiar with that. Can you say that one again?
Right. I think the whole purpose of allocating everything on the stack is to avoid memory management, rather than for any other reason. So as long as your data are allocated in a stack-like fashion, then you can get away with that.
Okay.
And I suspect that they are leveraging the fact that the shape of the data structures they can handle is not arbitrary. They always know how deep a given data structure is because they don't have recursive types. So every type they have has a fixed depth, and I'm guessing, I haven't figured out exactly how that works, but I'm guessing that that means that the algorithms that work with them don't have to allocate stuff sort of without knowing when they will free it. So you don't need any garbage.
Deterministic size stack. That's what to a certain extent.
The size of the stack probably depends on the size of the data set, but
or calculable.
Yeah, it can be calculated from the data that you're working on.
Yeah, right. Because you're saying basically if we're recursive, then
if you had arbitrary recursion, then my
can,
guess is you wouldn't be able to do that.
Yeah. Okay.
I imagine that the SDQL query that comes in, if you look at that, you can tell how deep your stack will need to be.
the thing I worry about is something like this, right? Where you have a temporary that, you know, it's a sum, and then you're creating, you know, a dictionary from it, and then you use that result to do another sum and create another dictionary. You would think this would be, which way does the stack go? Yeah, this would be more to the right of that, right? But then you want to pop the stack and get rid of this, right? And just leave that. But how do you do that in a stack discipline?
That's a good question, but you might know the size of
This
if you know
result.
yeah, if you know the size of the thing that you want to deallocate second, you could just pre-allocate the space for it. And then
That's true,
compute
but
the
you're not going to know how many of these key value pairs there are ahead of time, because that's the whole point of, I don't think you would know, right? Because you're doing this basically this group by and applying some function to the keys, and so I don't think you're going to know how many things are in it. It's not right, because it has to hold enough. It has
yeah,
to hold all the instances. It's not just a fixed size.
you have to look at the data set, but maybe there's a way to do that and then allocate the appropriate amount of space on the stack.
I would assume that they won't load the whole database into the stack in memory. They would just allocate. Depends on how the compiler is written, of course. They will just allocate kind of like a window, and then you grab some data, use the data, and after you're done, you grab another data into the same window, kind of like a moving window kind of idea, rather than grabbing a whole database. Database can be really big; it won't fit in the memory.
Yeah, those are techniques way beyond my expertise.
It's a very low level handling thing. I would assume if they want to allocate data in the memory, they have to do something about moving things around and then just keep the one they're using.
The stack that I thought they were talking about is, it's basically the call stack in C++, right?
I think so too.
You have free variables, you have variables in your, stack frame. And, and if that's an object, you can say, I want that object right here in the stack.
Yes.
Versus you can also have it as a pointer that then to a thing. But the stack also can control allocation and deallocation, I guess. So when you pop the stack, basically you run a struct operation on the object.
Right.
So that sort of means you don't have to garbage collect. It's sort of done in the stack discipline, but I'm still not sure how this works.
That is only your whole object is inside the stack. If you have interaction, like a pointer point to something else in a random location in memory, you still have to purge that and recycle that memory location. Otherwise, you will have memory leak in the future.
Right. But they have the notion of, when you destruct the object or the pointer to the object, it will then deallocate the object.
That is a smart pointer. I think C++ primitive pointer is pretty still pretty primitive.
Right. Yeah, you have to program in those destructor thingies.
With general memory management, or it's kind of taken care of if you use the stack?
Yeah, well, right.
No, I'm asking.
Stack is not a general memory management.
Yeah, so you don't have to worry about like memory leaks.
Garbage collection, right? You don't have to worry about garbage collection because you're not creating anything on the heap. But I think the reason why you can get away with a stack is because the language itself is a single expression without any recursive call, right?
Right.
And so at runtime, you have this expression that you're simplifying, and at any given time, excuse me, there's only one way. Like everything is determined. Whereas, with functional languages, if you call some kind of a function that has a closure and that references something that's outside of it and stuff like that, then you have to capture that, and then you don't know when that's going to be popped, so you can't do that. Whereas here, everything is finite in a sense that there's the sum operation, which ranges over some expression, which again is a simpler expression. There's no recursion there at all. So, it's well-defined expressions that get simpler as you go in. And I think that's why you can just, evaluate it in, in the usual way of operator, the operands are pushed into the stack, and then the operator is pushed into the stack, and then you pop it to evaluate what the result is, and then you push that down. So I think that's doable because you only have expressions that are in a sense finite, right? You don't have any kind of, like, the sum over e. E is again another expression. There's no way that e can become like arbitrarily big. There's no
Right.
while loop,
There's
right?
no general recursion.
Right.
But it
There's
is
not
a
even a
little,
while loop.
yeah. That
But it
sounds
could be a
exactly right.
dictionary of arbitrary size, right? You don't have a bound on the size of your dictionary.
That's right.
But
But
how
the
do you,
dictionary in the C++ code, the dictionary is just one variable, right? Like somewhere within
how
the
would you,
dictionary is,
yeah, how would you create a dictionary of arbitrary size in this language,
well, the
right?
dictionary is allowed to use, it's allowed to allocate memory dynamically internally.
But how do you define, okay, you need some kind of a variable pair ranging over something, right?
Right.
And that over E, like the X, the first line, or the scalar aggregation, you have the sum
Right.
value, key value in E. Well, how do you create E? Well, that has to be created from the primitives and so on. So I I could be wrong, but it seems to me that given the the base data type, we have defined, what is it? Yeah, if you start out with functions over the ints or nat, or is it dense int, you have to give it the upper bound, right? The dense int.
Hmm.
I guess you're just saying this, the structure of the expression is finite, but that doesn't mean the content. For example, if E values the dictionary, the content of the dictionary can be unknown still and infinite, or bigger than, or unknown to you at the time of your, until the time of your evaluation of the sum expression that's in your example. The
Right.
E is finite, but that doesn't mean the dictionary you're referring to is finite.
But I think you know how big the dictionary is once you look at the data set. That is, you don't have to, when you're compiling the C++ code, you don't have to hardwire sizes. You can have those be variables.
Yes.
Right. So, like, but E could be like one of their, relational databases, something like this that, you're getting from, maybe getting it from a database. So sure, maybe you can figure out how many entries are in the database, and so you can predict the sizes of all these things. But you're also given these functions G and F, which are going to be applied to the keys in this database, and you know, and depending on what the functions are, they'll end up with different keys here and then different values here. So it seems to me like it's going to be really hard to predict how big these things are without computing them.
But are these the functions f and g, are these arbitrary functions that you define? Because I don't
I
see
think they're
how you
being
can,
passed in over here, right? So
but
the
aren't,
group by is saying go through this table E and apply G in order to group them. You know, that will give you the key
yes,
for grouping, and F is then something you apply to the key to select the data out of it, I guess.
Right, but you
I
have
guess
a
my
limited,
point is that you can't define an arbitrary function in this language, right? There's no way to define a new function, which means f and g are just the functions that are primitive, that are already given, and the associated extensions of plus and times that are in the, that are extended to, you know, scalars and semiring operations.
Yeah, I think
right,
that's right.
yeah, you know what F and G are whenever you see this expression.
Right, right. That's why I'm thinking, you
Well,
know,
I think F and G here are, you know, they're functions that are defined in, you know, this other language, and you know that allows you to define functions. But yeah, once they're defined, you know what they are, and you know, for this particular aggregation, you know what F and G are, G and F are. Yes, you probably do know that, but without actually computing this, how do you know how big it's going to be?
There's probably some mechanism for computing that number based on G and F. I would think, but that's a very hand-wavy answer.
Mm-hmm.
They could be also be hand wavy in their paper. In the case with a lot of academic papers, they just say, "Oh, it's possible to do that because they think the structure of a language is finite. It's not enough from." But they might just be hand wavy about saying, "Hey, you can fit everything in the stack." But actually, I don't know if they really carry it out or is it just
Well,
they mention the idea.
they say they
Yeah.
have implemented it, so
Yeah. Okay. Okay.
I'm assuming that means it's possible.
Okay.
Right.
Yeah.
It may not be the simple model that I'm saying, just using the C++ call stack as their stack. Maybe it's like you said before, it's like some internal data structure that is stack-like. I don't know.
if you look at the definition, the denotational semantics on page 16, it seems like, you know, you cannot create an arbitrary, you know, indeterminate structure. Page 18,
Oh,
two
18,
more
sorry.
down, 18, 1-8, yeah, there. You see, if you look at the definition of the
Oh, wow. I
interpretation,
can look at this.
you notice that like the first line on the right, you can
Up
only
here?
do T, yes, you can only do T sub n, right? And so every time you create something, it's bounded by some finite n. And so that's how I
For
think you can,
records.
for records, yes. Now you can define dictionaries below that, T1 into T2. And then you can say, you know, it's defined to be this tensor, is that tensor sum? Anyway, disjoint sum A in the magnitude of T1. So this is where things can get a little hairy, is that if T1 is like the natural numbers, right? then are we talking
Mhm.
about, an infinite sum here? I'm not sure that that's what they're actually meaning, because none of their examples have that. So
Well,
So what do
it's
you, is this
potentially,
like a 10? Oh, go ahead.
sorry, no, it's potentially infinite. Um, so
but
like this,
any but right, but to create an actual dictionary, right, you can't provide it with a function, right? You have to provide the key value pairs.
yes.
So it seems like
When I say
that's why
when I say
it's always finite.
potentially infinite, it would be better to say unbounded. The size
Yes,
is
Yeah, they're always
unbounded.
finite.
but any particular
Right.
expression is finite. Yeah.
But at runtime, you know that it's finite. It has to be finite. Therefore, you don't need to allocate on the heap. You know what the size is. And then all the ones below it, they all are, E1
Wait.
through En.
Hmm.
Again, except for the summation, second line from the bottom. But then again, on the left-hand side, you have V1, no,
Where
above.
should I be pointing? This
Yeah,
one?
one line above that.
Like here.
Yeah. No, above that to the right.
Okay, like this one.
Yeah. Again, you have a
Okay,
record with N elements, right? And
right.
then if you look at the operations, on the left of that, it's E1 plus E2 or E1 times E2, again finite. And so when you create an expression from the bottom up, right, that's you're going to know at runtime how much to allocate, and therefore, stack, I think, is fine.
Mm. Hmm. Yeah, I haven't really looked at this, but it still feels to me like these dictionaries, have sort of unbounded size. They're going to be finite, but like if this is nat to record or something like that, you could have as many of those nat record pairs as there are, nats essentially. So you could have 10 of them, or you could have 100 of them, or 1,000. You don't necessarily know ahead of time, do you?
Right, but you're
Unless you're
allowed to
saying
look
that
at the
because, go
you're
ahead.
allowed to look at a particular dictionary before you do an operation. So as long as you can calculate the finite size of a result based on a finite input size, I think you know how much to allocate. And I think you can allocate it on the stack.
Okay.
Yeah, I think we're talking about runtime here, right?
Mhm.
We're not worried about compile time. So at runtime, the interpreter is looking at this expression, and it knows, right, how many elements it has, how many keys it has. So, allocating that on the stack, I think, is not a problem, but it may be unbounded initially, but when it's at runtime, you know how big the dictionary is, right? Because
Well,
there's
let's
no
go back.
recursion, there's no while loop. It's all built from the bottom up using finite sum and other constructors.
But if the dictionary is implemented as, I imagine, something like a hash table, right?
Mhm.
Which
But that's
is
the thing. There's no way to do that. The language doesn't allow you to define a function over the natural numbers as an alternative way of defining a dictionary,
right.
right? A
I agree.
dictionary is a pair, key value pair, and then you sum all those up to get a more complicated dictionary. But initially, you have to start with a single key and value. That's my understanding. Is
Yeah.
there a way to get to it that's beyond that? I'm not sure.
Well, you can have an explicit you can have an explicit dictionary, with 10 entries or something, and then that will be an expression that you then go on to use in other things.
You mean as a
Um,
function of the key?
No, not as a function of the keys.
Not an arbitrary
Okay.
function.
Yeah.
An arbitrary function. Where do we have that in the language?
We
Where you
don't
can
have arbitrary
define-
functions.
No,
There are no
Right.
such thing as a function in SDQL.
Exactly. That's why,
Yeah, I mean, they're pulling in functions from the outside here, which you can't define them in this language, but I guess you could define them outside and bring them in. That seems to be what they're saying there.
I guess my interpretation is that they're not. That's not an external function. It's just the functions that are provided by the data types, the primitive data types, and then the uh, uh, raising them into the semi-ring based on those
Hmm.
calculations that they gave of plus and times. Those are the only functions you have, I think. Because otherwise, I'm not sure.
Right, it would be, yes, a much more complicated system otherwise.
I think they mentioned briefly that there are other things, like trig functions are there probably, right? You can take square roots if you need to, stuff like
Right,
that.
but that's based on, if your underlying type is a real, for example, then you can do that, obviously. But apart from the functions that are given by the data types, that's, like page 5, for example, right? If you have real ints and nats, yes, you have all the functions over them. But you cannot create a new function that takes, let's say, 1, 2, 3, or the natural numbers into something else, and then say, oh, this is my dictionary. That's what I'm saying you cannot do. You cannot use a function, a general function, to define a dictionary that way. You can only, yeah.
Well, you can use this sum construct, right?
Exactly. But that's a finite sum. That's my point. Because you always have the definition, the third line, sum x in E. So you're already given an E. And how do you create an E? Right? Well, it's either a conditional or else it's a record.
Or it's
Or
another sum.
yeah. And again, that is finite because there you have to have those elements already there in order to create a new one.
Mm-hmm.
See, you don't have
But
a general generator that can just range over and create arbitrary size dictionary.
But like here for selection, well, again, I guess this P has to come from the outside. But the idea is, right, you're going through this relation, applying this function to the keys, and only if it's true, do you add that element back into the relation. And
Right.
if you
But
don't know what
P,
P is, or even if you know what P is, you can't really figure out how big this is without doing the whole computation. Do you know what I'm saying?
yes, but it has an upper bound though, right?
Right, which is the size of
Because
the economy.
right.
Yeah. Okay.
Because
I see
P
what you're
can be
saying.
it can be a filter, right? It reduces the number
Right.
of elements, but it can't increase it, right?
Right. That's true.
Yeah. And then the one below it, the F there, again, you can do computations on it to get a new value in whatever the type X dot key is. But again, you cannot create new elements to make the dictionary bigger. Right? So
Okay.
so knowing the size of R, we now have the size of the sum of whatever the body of the expression is. You cannot make more. And that, I guess
Right.
that's
So
my
you're
point.
saying it's more like we have a bound on the size.
Yes.
So if we have a bound on the size of R, then we have a bound on the size of this. It might be less because
Yes.
some of these Fs might go to the same value or something.
Right. And then
Um,
they collapse, but
then
yeah,
they collapse, but it gets smaller. And
right.
I guess for the rest of these, it's the sort of the same thing. You have a bound on the size of R and S, so you know that when you do the Cartesian product, there'll be a bound on that.
But
Right.
Okay.
I do feel like there's a difference
Still,
between the number of values in a dictionary and the size in memory. Right? I assume that these dictionaries again are going to be hash tables. I'm sorry, yeah, hash tables.
Right. Yeah, they could be
So,
nested
Mhm.
in the nested relational calculus. But again, they're finite in the sense that they're determined. When you have a dictionary, you can recursively go down all the way down to the primitives, and that's it. You know exactly what the size is, right? There is no
hmm,
place where you have to say, I don't know how big this dictionary is because it's using a generator, you know, and I don't know when that generator is going to stop. No, we don't have that. We only have finite constructors over finite things.
hmm. But you have to, yeah, but you can't predict this at runtime. I think we agree on that, right?
You can't predict it at compile time.
Right. But at
You,
I
runtime,
mean,
the
what,
data
did I
is
say the
there.
wrong thing?
yes,
Yeah, you can't predict it at compile time
right,
Correct.
because, right, you might be reading in, your
Yes,
data from a database and you don't know how big that's going to be at compile
correct.
time, but I guess you do know at runtime, and therefore maybe then you can put bounds on everything else.
Hmm.
Why do you even care?
Well, we're trying to get these things to fit in a stack, I guess.
Right.
I
Because
mean,
they
because
claim
shouldn't that
that
be something that you don't have you wouldn't want to worry about though?
Say
in
again?
general, in general, no, but the whole point of this paper is that they can run these computations using this language more efficiently than other techniques. And one of the arguments is the efficiency is the memory layout, and that implies that they don't have to do garbage collection because everything can be done using a stack-based allocation.
right. But that if you are the user of their system, that's invisible to you, whether they
Right,
what kind of memory management they are using or not using. So if you were writing
right,
this code by hand, you would definitely want to use an automatic memory manager because then you don't have to think about it. But they are generating optimized code to do it for you.
So we don't, as a user, doesn't we don't care, but for them, the implementers, they obviously care.
Right.
right, right.
Okay.
So they figured it out somehow. And
Yes.
there's not enough information here to really know how.
Right. My guess is that there are probably other papers on database operations that would tell us how they did it, but that's probably kind of far afield to go looking
Yeah.
for answers.
Yeah, I mean their bibliography is huge.
Mhm.
So it would take us forever to read all those papers.
Right.
Not that we need to, but we might have to figure that out.
Yes. But it's probably not our primary interest.
Right.
Your guys' main takeaways from this?
Good question. My main takeaway from this is that if you carefully design a language that is functional, in other words, there's no side effect, then you can get a pretty expressive language that looks like SQL and is efficiently implementable. That's their whole argument, right? By carefully defining the data structures, the semi-ring modules, and you have a language that expresses that using the lets and sum, then you can do a lot of the operations that other databases can do, but you can do it more efficiently because you can, allocate things on the stack and stuff and like that. Optimizations, the loop nesting and the various optimizations can be applied. Whereas if you started out with a general SQL, you cannot do those things because there's a lot of side effects going on.
Right.
And so,
You have in more general SQL, you have data types that don't obey laws that allow specific optimizations. So
right,
yeah, each place where they are talking about the laws that that semi-rings and semi-ring modules obey, those are the things that they use in doing the optimizations. So like it's in section 5, they talk about a bunch of the operations that they optimizations that they do. And
right,
those optimizations, I think, are all based on those laws. And so I think that's why this paper attracted Sergey's attention to begin with, because he's interested in things that obey well-defined laws and the consequences of obeying those laws.
right,
Right. So, right, they have a bunch of these optimizations where, because a lot of these data structures are things like, a dictionary where the keys are these complicated things, and then the value is just like 0 or 1 or a number or something like that, which doesn't seem like a very efficient data structure, but I guess they have ways of representing them more efficiently, and then using some of these different fusions to kind of
So how do
get it
you
down to
know,
a simpler form.
how do you determine, I guess, your inputs that fall within the domain of this so that you can use it?
Well, they're sort of saying you can use it for, like relational databases and linear algebra kind of things. So
Like
I guess,
like basically what qualifies valid input? That's kind of, how do you determine that?
Well, it has to have the form of one of the data types that they support. And so you have to be familiar with your domain enough to know whether your data can be phrased in that way.
I guess it can't be a totally generic document database, for example.
right.
Anything with a tree structure of arbitrary depth is probably not suitable.
Yeah. You need to be able to describe the types.
Yes.
Okay.
Right.
You need to know what you're doing.
But it's a good
Mhm.
question. Like what's a data store that we worked with which would not be amenable to this approach?
Oh, nice. That's a nice question.
I
Yeah.
think anything that stores, for example, arbitrary syntax trees for a programming language.
Because again, those are trees and they require recursion.
Yes.
But
Yeah.
is there something that doesn't require recursion that can't be
Right. Well,
handled by this?
yeah, the things like the gene databases that they're talking about, genes can't contain other gene databases. So that's a relatively flat data structure.
Right. But they allow the nested relations where
Yeah,
a
yeah.
relation can have another relation in it.
Yes,
But
that's it
still,
to a
it's a
fixed set.
fixed number of
Right.
levels. Yeah.
Right. So
But I
the
guess there are things like strings that just aren't aren't semi-rings. And so once you start getting data in that's like a string, then you can't use any of these operations like multiplication. Maybe you can,
right,
maybe
right.
plus is concatenation, but you know, it would be fairly artificial to do multiplication. Like maybe it would mean creating n copies of the thing concatenated together or something. But you know, you can't. So I think there's data that doesn't fit this mold. String is maybe a simple example, but
Something
Right.
like a regular expression search, we would not be able to do, I think.
say
Right.
again, a what search?
Sorry, a regular expression search, like a string processing stuff, probably would not work here. So like with a SQL query, you can search for all of the records, you know, whose column 2 contains this substring. I don't
Oh, I see.
think we can do that here.
Yeah. You'd have to bring in the function that does the regular expression from the outside. You can't define it in here. But I guess once, if you've
Oh, maybe you can.
written it outside the system
I
and
don't know.
bring it in, then you could use it to filter.
I guess you can. I guess you can use it to like project and filter and stuff. So I guess I'm wrong about that.
So in,
Jumping to the conclusion here, the performance that they show, this is like page 21 and following. It is impressive that they're able to achieve speed up relative to other systems, and that's nice. But then I was looking through, I did not see what their space requirement was, because it's always a trade-off between space and time. And I'm just wondering, did I miss it?
hmm,
Because it seems to me that their data layout and the functional approach may require more memory usage, but you know, I don't know.
Right. This comes back to the question of how can the data be windowed if
Yeah.
they do something like that? And that is something I have no idea about.
Hmm. Yeah. But as far as I can tell, and I haven't read every word, but just looking at the graph and looking at the descriptions, they don't talk about memory usage during runtime. And to me, that would be an interesting factor because if you're dealing, their system is pretty modest, right? They have an iMac, they run it on an iMac with 32 gig of RAM.
Mhm.
And I'm thinking, okay, if everything fits into 32 gig of RAM, that's great. But once you get beyond that, I'm wondering, for large data sets, and you have to distribute it and stuff like that, then it might be a different issue. That memory requirement may make it more difficult. But still,
Right.
their speed up is impressive. You know, the optimizations that they're able to do, reduces a lot of complex nested stuff into kind of a flattened, operation because you can fold a lot of these things and so on. So I think the specific technique is impressive.
Yes.
yeah, here they, oops, no, no. They do talk about like whether things are in the cache and things like that. So I guess they work pretty hard at dealing with some of the memory issues
Mm-hmm.
so that like unused columns are not read into the cache. using this special columnar layout.
Mhm.
Yeah, but yeah, that's oh, I see. So this is these big ones, I guess. That's your sort of standard dictionary that you might do. But then they use a row store and that makes it smaller. And then this column store brings it down even lower. And I don't know what these are, but
Yeah,
other representations.
Typer and Tectorwise are other applications that are out there, I guess. And so these are the relative speeds.
So like kind of dictionary, I mean, kind of database store kind of things.
Yes, I think so.
Okay.
Yeah, on the left paragraph, it says, two state-of-the-art analytical query processing engines. One is Typer and the other is Tectowise.
Okay. Yeah.
So,
So,
the other
yeah.
systems are still faster than them for some of those cases. Like the blue is Typer is faster. And so they kind of say that, better memory management, they could be even better now. So that may be true. But anyways,
But they're in the same ballpark, it looks like, at
Mhm.
least with their column store. So if
yes,
it's easier to write the code and think about it, maybe it's worth it.
right, exactly. So that's
Yeah.
basically my takeaway is that if you start with a nice language, which is functional, and you can be pretty expressive and still get good performance if you know how to do these memory layouts properly. So that's the name of the game, I guess, in this field.
Yeah. I guess my takeaway is, more from the language side. It just seems really cool that they can have this sort of one, the semi modules, and then represent lots of different things as semi modules. But then you have all sorts of operations on semi modules, like, multiplying one semi module times another and things like that. And it's just all kind of orthogonal, and seems like it's like pretty powerful when you kind of use all, I don't know. But just from the language point of view, I think it's kind of cool that they can represent these different things in the same framework,
Right.
and then
Yeah.
have fairly interesting operations on those things.
Right. A fairly small framework with some well-defined laws that lets you do that you can permute in all of these different ways.
Right. Okay. Still
So,
have half an hour. Do we want to switch gears or what?
yeah, why don't we switch gears? Does anybody else anything to say about this paper, or are we ready to hop back to SOFP?
Fine with me.
Okay, then.
Let's see if I have it here. Oh wait, the draft is more recent.
Right, the September 2023, right, is the version you want?
September 30th. 23.
Mhm.
So let's see, what can you give me an idea what page we're on? Oh, I guess I can find.
Well, it's definitely chapter 13.
Right. So we were around section 13.2 or 13.3. Maybe
Okay.
it makes sense to review like the last couple of sections of subsections of 13.1.
Okay, so this is 13, right? 13.1. Okay. So he's basically saying, okay, here's how we create this DSL thing. And then
Right.
refactoring it
Two,
to a
Right.
monadic
yeah.
thing.
2 examples of DSL. One is for reading files, and the other one is for complex arithmetic.
Right. And then did we go through these recipes?
Hmm.
Right. So he's basically doing it here as sort of a trait, and then separate classes for each of the operations, path and read.
Right.
And then you build up your DSL in terms of these things. And then you
Right. Each of
have
those
a runner on it.
yeah. In Haskell, each of those case classes would be a constructor. Would have a single data type that represents all of the related operations. Scala case classes would translate to Haskell constructors of that
Right.
data type.
Where prog file is your inductive type with
Right.
path and read as constructors. Is that what you're saying?
Yes.
And it's basically a GADT because these result types depend on the stuff that's inside.
Yes.
I don't know what my note was there. Run is not monad. Oh, run is not in monad DSL. Well, anyway, technicality, I guess.
Hmm.
Okay. Ooh, I don't know what all these markings are. Oh, I guess I was marking where he's defining things. No, I don't know. Ignore my markings. Okay. Anything to be said here? I don't remember it well enough to go through it. So is this the second way of doing things? No, this is the same thing.
Right. These are all part of the same extended example. I think it's right. Section 13.2, where he's talking about the different encodings of the free monad. So that then there's different ways of doing things.
Right.
So he's
So the
gone
first
through,
section was motivating the notion of a free monad, I guess.
right. Basically, he goes through and he abstracts out more and more general purpose stuff until finally you're left with nothing but the free monad, which is sort of free of anything specific to a particular monad.
Yeah. I almost think of it like as a base class for monads. It's sort of like your other monads will inherit from it. But
yeah, kind of that.
but and yeah, but instead the free monad basically has a place where you can plug in the specific stuff, I
Yes.
think.
So, but the free monad is more of a concept than a specific piece of code. And so that's what Sergey is trying to show here. He actually gives 4 different ways of implementing the free monad. And
Right.
then his mission, should he choose to accept it, is to show that they're all equivalent.
Mm. And you're sort of saying that the monad is sort of a concept because each of these things sort of implements sort of different parts of it. Here you get pure and flat, and
Right, but you can convert among all of these different ways of implementing the free monad.
right.
And so
And so
you
is
can,
this his general one? Or go ahead.
I think they're all general. And in fact, I think the effect handler paradigm that we are studying is actually a 5th way of implementing the free monad.
Hmm. Hmm. I'll have to think about that.
So
But this one, it's like each of the monadic operations creates basically a node in the tree. Val,
right,
bind,
right,
fmap, and op. But then you do have flat map and map as operations, not nodes. Although bind is kind of like flat map. So
right,
no.
yes. But
Actually, flat map does just create a node.
it just
And so
returns
does
that,
map.
yeah. Yes,
Okay. Just other ways of creating nodes. So you basically, your free monad in that case is just, you have a node for each operation. So when you build up your monad using monad operations, you're just building up this tree. You're not, and it's not specific to the kind of data you have.
right,
Just represents your expression direct as a monad.
right,
But then you do have a runner, and here's the place op. Right. So op is the thing that you get to bring in. I think that's related to the F. And so that's where you bring in your domain specific operations. And here is where you pop out and run those domain specific operations. And I found this code really confusing because the runners and run, there's more than one. Like this run isn't the same as that run, I think. So it would be nice if they had different names, maybe, but
Maybe a question related to that from this
yeah.
point of view. The equation that we saw that the operation must obey, like this kind of algebraic effect must satisfy.
Right.
Where are these relations or equation expressed? from this construction.
So you're talking about the monad laws, like
Right. I guess that the monad must satisfy a kind of general laws for the monadic laws, but uh, actually, I have not clear in mind how this construction is somehow equivalent to effect handlers, or how these two relate to each others. But we saw that algebraic effect must obey a number of equations, right? Must satisfy several relationships, right? Like with through the computation tree, and related to that, if we wanted to construct a monad for handle the effect, instead using effect handlers, from dealing with that in such monadic way, how the equations or the relationship from the effect should be included in this construction, monadic construction.
Right.
Right. It could be some extra laws or equation that the monad should satisfy somehow.
Right. So there's two types of laws that you could potentially think of here. One is the general monadic laws that apply to all monads. And then again, there are laws that might apply to a specific monad. Like the laws for the I forget which example it was in the
for state, for instance.
Right.
Well,
Yes.
but if you write and then read, you get what you wrote.
Right. And so, yeah, so those are both interesting. And then as Sergey points out here, all of those laws apply only after you run the monad. So the actual data structure that you are building for the free monad, depending on which encoding of the free monad you are using, the laws may not apply to the encoded version, but they will apply once you run the encoded version.
Right.
Okay, so I'm not sure that I understand. Could you elaborate a little bit more about that? I understood the words, but I have not clear in mind how this. So,
Well, for instance, you can use this bind node, right? It takes two other, instances of the free monad. So you could have bind and then, passing val. And you're creating this tree with a bind and then a val version. And then there has to be, another functional kind of thing. But it's just a tree. And the law says if you have bind of return, basically if you do return and then flat map of F, or bind of F, then return bind of return A F should be just F of A, right? It should calculate out, but this is just a tree. There's no reduction that's going on until you run it, and then you'll see that for any possible way to run it, you'll get that. You'll get those laws. I don't know if that made sense.
okay, more or less. And the okay, but it could be different from different encodings. You say that the laws could have a different appearance, or I mean, from trying to handle a given effect, I I understand that the loss comes from the effect itself. Like we have we want to manage something that satisfy these given rules, and it sounds. I believe that the rules should be fixed or should be the same, uh, not depending of the way we run the. I don't know, and maybe.
Well, I think I understand what you're saying. So, like, if we were to use this monad for effects or something, then this op is the place where you bring in stuff from the outside, right? So we would be bringing in maybe the trees for get and put on, for state, and those nodes might have their own rules, so that if what you're passing in is a tree with get after put, however that looks, that should be the same as just getting the thing that you put in, whatever, however you express it, right? And so again, you would probably have nodes coming in here, but the rules would be sort of on the value. So it's not until you run it that you would actually see that those rules held.
Right. So the laws are phrased in terms of equalities. One expression equals another. So in this case, the equality is just quotiented by running. So that's yeah, that's I think a proper mathematician would not consider that to be cheating.
It's sort of an observational equality.
Yes.
It's like, these things are observationally equal because there's no way to write a program with run where you can tell them apart.
Well, you can actually examine the raw data structure and tell them apart, but yeah, once you have, you can't distinguish.
Right.
Hello guys. I just have a few minutes. I'll have to return to my parental duties probably very soon. Just a comment here. So I don't want to pretend that the laws hold observationally or in some sense. I just want to say they don't hold if they don't, right? So they don't hold for specific encoding. But at the same time, we can prove that they hold after you run, right? So this is always true. It's not sometimes true. So, and this is general. This is for any type class for which you make a free version, which has a tree encoding and some other encoding. There will always be the same situation that for certain laws may not hold in the encoding, and yet they will always hold once you run. This is a consequence of the general properties of this construction. It is not accidental. It's always going to be the same. So I prefer just to say, well, here's an encoding where this law holds, but this law doesn't. And because some encodings do satisfy some of the laws, but not all. And so I would say, well, in this encoding, these are the laws that hold. These are the laws that don't. And then I would say, well, that's once you run your tree and interpret it, then they will hold in the actual result that you
Right.
get. So that means you
Do you think of this?
Yeah.
Do you think of this at all in terms of sort of like intentional versus extensional? Like an intentional function, they can have a different expression. So like
Yeah.
their actual form is different, but extensionally they're equal because when you apply them, you get the same result. To me, this is intentional up here. This
Okay.
is your
I have
raw
to,
data structure, and it might be
yes, that's
different,
true.
but when you actually run it, then it ends
Yeah.
up being the same.
Yeah, that is a possible interpretation. I have to drop off now. I'll be back maybe.
Right,
Okay.
right. Pete's interpretation is that, you know, the free monad basically gives you a syntax tree for a monadic expression, if I understand it. And
Yeah, I
so
think you're
just
right.
saying that these two expressions are equivalent because they evaluate to the same thing, where the evaluation is the running.
Yeah. Sorry. Okay. Raw tree encoding, reduced encodings. Oh, so here, I guess he's writing some functions between these different representations. So this goes from that fourth one to the third one.
Right.
And the third one was this one, right? Yeah. Where you have nodes for pure and suspend and flat map. Suspend is like op, I think.
So
Yeah. Whereas this has nodes for val bind, flat map, I guess.
I think that's actually functor map.
Oh, functor map. Yes, just plain map.
Yeah.
And op. Right. Right. Functor map. Yeah. So this has an extra node compared to this one for basically, I guess that functor map is the extra one. Although
Right.
maybe the form of op is different. But anyway, so he can convert. Yeah, so we're basically taking the functor map and using the law to create the version that uses bind or flat map by passing in pure, also known as return.
Yes.
And then this is 3 to 4. Pretty straightforward since 4 kind of has all the nodes corresponding to what's in 3, although I thought 3 had suspend instead of op, but
Yes.
yeah.
But
But it's basically the same idea.
basically the same thing.
Yeah. And then I guess the runners you just translate the thing and then use the runner for the appropriate monad, whether it's 3 or 4.
Right.
And then here's 2 to 3 and 3 to 2. Oh, except we don't know what this is.
Right. So yes, I guess this is where we see this
Focused.
chapter is not quite finished,
Right.
but
2 is this one has returned and bind, which should be enough, but
right. So the relationship between this and the event handlers is that in an event handler, you have the it's like a pattern match on the free monad, except that you for each op, you have a special case for the bind of that op. So it's as if you I guess it would be the an encoding where you have a val, which is the return, and then a bind op constructor, which folds together bind and op. Something like that.
right. So you'd have return or val, like you said, and but then each op would, you might not have bind as it's a thing itself, but
Right,
basically each op would sort of do the bindish kind of thing.
right. I think that's what we're seeing when we look at those handlers.
Yeah, I think so. I'm just not sure if there's really a bind or not. I thought there was, but
I think there might
maybe you.
right. I mean, you might be able to define an op that sort of does a vanilla bind that doesn't, an operation that doesn't have any semantics of its own. Does that make sense? I'd have to think about it.
Yeah. Okay. Well, we're kind of running out of time.
Yeah, so this is, I guess, probably a decent place to stop. So the next section, 13.3, is talking about free constructions for other type classes. So that is other than monad. So yeah, so there's quite a bit here because there are quite a number of type classes that we've talked about.
Yeah. I wonder if it has like semi-rings.
No semi-rings.
That's our homework. We need to do this for semi-rings, semi-ring modules, whatever.
Yeah. But anyway, should we pick up at section 13.3 next time?
Okay.
Okay. And
Sure.
is 2 weeks from today good?
Yeah.
Mhm.
Looking forward?
Yeah, I'm not sure about that day, but I'm not sure about the next weekend either. So let's just go with the 24th.
Right. We can always reschedule. So, all right then. Well, I guess I will see you all in a couple of weeks.
All right.
Thanks
You
again.
guys, thank you.
Thank you.
Thanks. Bye.
Okay, till next
See you.
time.
Bye.